Okay, so now we're going to talk about the relationship between the Gibbs free energy that you were introduced to the last time and what we learned about equilibrium. So turns out that there's a relationship between the free energy of a reaction and the reaction quotient. If you remember, that is basically the product of the concentration of the products divided by the product of the concentration of the reactants at any time, regardless of whether or not the system is at equilibrium. So this is the relationship right here. Delta G, which is a free energy, is equal to the standard free energy plus RT ln Q, all right? So, and again, R, in fact, I think I should have it down here. R is 8.31 joules per mole Kelvin, which is another way of stating the molar gas constant. T is the temperature in Kelvin, of course. And Q, as I said before, is the reaction quotient, all right? And now, let's talk about what happens at equilibrium. So, if we're at equilibrium, there are two things that will be happening. One would be that delta G would be equal to 0, all right? And the reaction quotient would be equal to the equilibrium constant K, right? So if we put 0 here where delta G is, and K where Q is, you're going to end up with this equation right here. 0 is equal to delta G standard plus RT ln K, and we can rewrite this as delta G standard is equal to minus RT ln K, right? So that's the relationship between the standard free energy and the equilibrium constant, all right? So that's a very important equation, which I think will be, well, I'm quite sure there is at least one question in the assignment which deals with this, all right? Okay, so that's a relationship, a very important equation which you need to be aware of. And if I'm not mistaken, this equation is also in the tables, all right? Okay, so that's that. So just to graphically represent what we just discussed here, this or these are two graphs where we plot the free energy of the reactants on this axis here, the free energy of the products on this axis here. Same thing for the other graph. The difference is that in this particular case, the standard free energy would be negative, whereas in this case, the standard free energy would be positive. So what that means in terms of the appearance of the graph is that the free energy of the products, in this case, for the graph on the left, in this case, the free energy of the products would be less than the free energy of the reactants. And the opposite would be true in the case of the other graph, all right? So for a reaction where delta G is, the standard free energy is negative, on this side of the graph, Q is equal to K, so therefore, basically, it's not at equilibrium. So basically, the forward reaction will progress until you get to this point here, where the energy would be a minimum, the free energy would be a minimum. And in this case here, Q is equal to K, right? So this represents the equilibrium position. If you drop a vertical line down, where it cuts the x-axis down here, then that represents the equilibrium position. So basically, what this shows you is that if delta G is negative, that means that the equilibrium position favors the products because it's closer to the products side of this particular axis right here, right? And over here, the reverse is true, right? If you have the reaction starting and then it progresses, Q is less than K in this region here. When Q is equal to K, then the equilibrium position will be closer to the reactants, right? And that's what happens in the case of a situation where the standard free energy is greater than 0, all right? So that's basically, you know, as I said before, these are graphical representations of the relationship between the free energy and the equilibrium constant and the reaction quotient as well. All right, so just to emphasize the relationship between the standard free energy and the equilibrium constant, we see here that if K is greater than 1, and you can look at this equation here to figure this out, if K is greater than 1, then of course ln K would be positive. And if ln K is positive, then because of this negative sign, delta G standard would be negative, all right? So basically, if K is positive, the free energy is negative, which means that the reaction would be spontaneous as far as that is concerned. And as stated here, the products will be favored over the reactants at equilibrium. Now, if K is equal to 1, right, we all know that ln1 is equal to 0, right? Which means that the free energy will be equal to 0. So therefore, that's why it says here, ln K 0, free energy 0, which means that in that particular case, the products and reactants are equally favored at equilibrium. And then finally, if ln K, or I should say, if K is less than 1, that means that ln K would be negative. And because of this negative sign, that means that delta G standard would be positive, which means that in this particular case, the reaction would be, under standard condition, would be non-spontaneous. And another way of saying it is that the reactants at equilibrium will be favored over the products in that particular situation, all right? So that's basically, you know, a sort of qualitative way of describing the relationship between the free energy standard and K, and the possible consequences of different situations where K is greater than 1, equal to 1, or less than 1, how it affects the standard free energy. Okay, one last thing I want to talk about here is the fact that all that we have discussed so far applies to several systems where, you know, chemical reactions takes place, right? And I'm thinking in particular biological systems, and also if you're interested in engineering, a lot of what we discussed in this chapter will apply. So just to give you an idea as to one particular situation where free energy considerations play a role in understanding certain biological processes. So what we're trying to discuss here is the synthesis of proteins from amino acids. So I don't know if you have met this in your biology courses, right? But amino acids are basically the building blocks which come together to form, well, proteins eventually. It will form peptides first. And if I remember correctly, you have their primary structure, the secondary structure, and tertiary structures, and so on. So if you look at the thermodynamics of the formation of proteins from amino acids, what you'll find is that this is basically a non-spontaneous process. And just to give you a simple example of 2 amino acids coming together to form a peptide. This is alanine plus glycine, and it gives you the peptide alanyl glycine. If you look at the free energy of this reaction, it's positive, right? So therefore, what that tells you is that this is not a spontaneous process. However, we know that this can happen in biological systems. So the question now becomes, how does that happen? Well, in order for you to drive a spontaneous process, energy would have to come from somewhere in order to achieve that, right? And in the case of the synthesis of proteins, or in this case, this particular peptide, the energy will come from a reaction of a molecule known as ATP, which I'm quite sure you probably met in your biology courses, which would basically lose a phosphate ion and also lose energy to form ADP, right? So the energy that is produced from this reaction here is used to drive the formation of proteins from the smaller building block units of amino acids. So the question now becomes, okay, so how does ATP get its energy? Well, that's where the glucose metabolysis comes into play, because what happens is that through several steps, of course, very complex and so on, the glucose will be converted to carbon dioxide and water when it reacts with oxygen, right? That is an exothermic process. So the energy that is generated as a result of the glucose undergoing the reaction to form carbon dioxide and water is used to convert the ADP to ATP, right? So basically the overall picture is that energy is provided by the glucose according to this reaction to convert the ADP to ATP, and then the ATP will lose energy to form ADP, and that energy is used to drive the non-spontaneous reaction of amino acids forming proteins. So basically there's a coupling of this reaction with this reaction, and the result would be a spontaneous reaction. So this is the equation which basically represents the coupling of the ATP to ADP reaction with the synthesis of proteins from amino acids. So this is the equation here. And if you look at the actual free energy value of this, it's negative, right? And therefore, the coupling results in the formation, in the spontaneous formation of the peptide from the amino acids. Without the coupling, that reaction will not take place because without the coupling, the reaction is non-spontaneous, all right? Okay, so that's just one example of the application of the principles that we discussed in this chapter. And that is in the case of the synthesis of proteins. Okay, so that's basically it for this chapter. Check something here. So, oh shoot, I just realized, anyway. I printed some copies of assignment 7, but I forgot to pick them up, so I might have to run upstairs. Let me just do one last check of these questions here. All right, so I think I told you guys to try those questions, the rest of the questions in the assignment, so I'm just going to leave that for you guys to attempt. Again, if you have any questions, please feel free to either come by my office during office hours, or you can call me on Skype and we can discuss that. All right, so the next chapter we're going to talk about is dealing with the topic of electrochemistry. And as the name suggests, or the title suggests, we're looking here at basically the intersection of electricity being involved in either driving a non-spontaneous reaction or a spontaneous reaction which produces an electric current or electrical energy, right? So these are the two types of electrochemical processes that we'll be looking at in this chapter. There are two categories. The first category is where energy is produced, electrical energy is produced as a result of a spontaneous reaction occurring. And then the second category is where we use electrical energy to drive a reaction that would be otherwise non-spontaneous, all right? Now, all of the types of reactions that we'll be looking at in this particular chapter are redox reaction. And of course, by now, especially if you have had me in Chem 1, you should know what a redox reaction is, right? Redox, of course, is abbreviation for reduction and oxidation, right? And you should remember that oxidation basically involves the loss of electrons and reduction involves the gain of electrons. In my class in Chem 1, I introduced my students to this memory tool, oil rig, to help you to remember what is involved in redox reactions. Oxidation involves loss of electrons, reduction involves gain of electrons, all right? So that's basically what redox is all about. So just to show you a simple example of a redox reaction, the reaction of magnesium with oxygen to form magnesium oxide. If you look at the changes that are taking place in the case of each atom, in the case of magnesium, magnesium here is converted from the magnesium atom to the magnesium ion, right? So therefore, we can write down this half equation representing the change that magnesium is undergoing. And then as far as the oxygen is concerned, it is also undergoing a change where the oxygen molecules will be converted to oxide ions, right? And we can write down another half equation in the case of the oxygen gaining electrons to form the oxide ions, right? So this first equation here would be oxidation because the magnesium is losing electrons, and the second half equation here would be the reduction half equation because the oxygen is gaining electrons, all right? And this is what happens in every redox reaction. Something is losing electrons and another species is gaining electrons, all right? So that's what happens in any redox reaction. Okay, so this will be a bit of a review, especially again, if you have had me for Chem 1. In order for us to identify whether or not a reaction is a redox reaction, one of the things that we can look at is what we call, is a change in what we call the oxidation number. So the definition of the oxidation number is given right here. It says that the oxidation number is the charge that the atom would have in a molecule or anionic compound if the electrons are completely transferred. So this is basically used as a tool to measure the degree of oxidation that is present in a particular atom, whether or not it's by itself or in a molecule. So what we're going to do right now is, as I said before, this is going to be a bit of a review. So, this should look familiar to you. But we're going to go through some of the rules for determining the oxidation number of an atom in a molecule or ion, right? And the first rule, which is probably the easiest to remember, is that free elements that are not combined with anything else, those atoms in that element would have an oxidation number of 0, right? So oxygen by itself, carbon by itself, silver by itself, any element that is not chemically combined with anything else, those atoms in that element, in that state, would have an oxidation number of 0. So these are just some other examples: sodium, barium, even the diatomic or polyatomic molecules, as long as there are no other elements involved, the oxidation numbers in all of these cases is going to be equal to 0. Now, the next rule has to do with monatomic ions, right? These are ions that are formed from one atom. And basically what this rule says is that monatomic ions, as far as their oxidation number is concerned, will be equal to the charge of that particular ion. And I think I have some examples here. So for example, in the case of the lithium plus ion, the oxidation number of lithium in that case is +1. In the case of the iron 3 ion, the oxidation number of iron in that case will be +3. And in the case of the oxide ion, the oxidation number in that case will be -2, all right? Okay, so here we get to rule number 3. Rule number 3 says, and this rule, by the way, specifically deals with oxygen when combined with other elements. In fact, I probably should add that little statement here. Where am I going to add that? The oxidation of is usually -2 in their compounds. So let me put here in their compounds. All right? So in other words, if oxygen is in a compound, right, then the oxidation number of oxygen in those compounds is usually -2. Now, there are some exceptions. And the exceptions, well, one of the exceptions would be hydrogen peroxide, and the other exception would be any compound that contains the peroxide ion, right? So therefore, if you have hydrogen peroxide or any peroxide ion present in the compound, the oxidation number of oxygen in those compounds will be -1. But otherwise, if oxygen is combined with something else, like hydrogen or metal, then the oxidation number of oxygen in those compounds will be -2, all right? So that's rule number 3, right? The oxidation number of oxygen is usually -2 in their compounds, but in peroxides and in hydrogen peroxides, the oxidation number of oxygen is -1, all right? So that's rule number 3. Rule number 4 has to do with specifically hydrogen, right? And according to this rule, if hydrogen, again, I should add the same thing I added in the previous oxidation in their compounds. So let me put here in their compounds. All right? So the oxidation number of hydrogen when combined with other elements is usually +1. But again, there's an exception. And the exception is if the hydrogen is bonded to a metal in binary compounds, then the hydrogen in that particular situation will have an oxidation number of -1, all right? So if hydrogen is combined with most other elements in their compounds, then hydrogen will have an oxidation number of +1, excepting where hydrogen is bonded to a metal in a binary compound. In those situations, the hydrogen will have an oxidation number of -1. Let me see, do I have any examples here? No, so let me give a couple of examples. So for example, in the case of H2O, the hydrogen oxidation number would be equal to +1. However, in the case of calcium hydride, in the case of sodium hydride, the oxidation number of hydrogen is -1, all right? Because in this case here, hydrogen is bonded to a metal in a binary compound, all right? So that's rule number 4, specific to hydrogen, +1 in most of their compounds, but -1 if the hydrogen is bonded to a metal. Okay, so that is the 4th rule. The 5th rule deals with group 1A metals. again, in their compounds. I keep having to add that. Right? So in their compounds, the oxidation number of group 1A metals is always +1, for 2A metals, always +2, and for fluorine, and this is very specific, if fluorine is bonded to anything, the oxidation number of fluorine is assumed to be -1, all right? So that's rule number 5. Group 1A metals like lithium, sodium, potassium, and so on, when combined with other elements, the oxidation numbers is +1. Elements such as magnesium, beryllium, calcium, and so on in group 2A, when combined with other elements, the oxidation number in that case would be +2. And then fluorine combined with anything, fluorine in that particular situation will have an oxidation number of -1. Okay, so that's rule number 5. Rule number 6 has to do with situations where you're dealing with a molecule or ion. And basically what this rule says is that the total sum of the oxidation numbers of all the atoms in a molecule or ion is equal to the charge on that molecule or ion, right? So it doesn't matter, you know what the elements are. When you add them up in terms of the oxidation number, according to the formula for the compound, the sum of the oxidation numbers will be equal to the charge, whatever the charge is for the molecule or ion, all right? So based on that particular rule, we can answer a question such as the one that we see here. What are the oxidation numbers of all the atoms in the bicarbonate ion, all right? So based on the previous rules that we discussed with respect to hydrogen and oxygen, we know that hydrogen will have an oxidation number of +1, and the oxygen will have an oxidation number of -2. We know that already because of the rules. I think it was rules numbers 2 and 3, if I remember correctly, right? But the rules do not give a direct answer as to what the oxidation number of carbon is. However, based on rule number 6, we know that the sum of the oxidation numbers of all the atoms in this formula will be equal to the charge, which is -1. So basically, we can set up an equation based on that, right? Basically, we can add the total oxidation number of the 3 oxygens, so that's 3 times -2, plus the oxidation number of the 1 hydrogen, which is +1, plus the oxidation number of carbon, which we don't know. When we add up all of that, that will be equal to the total charge on the ion, which is -1. And therefore, all we have to do is solve for the unknown. And when we do that, you'll see that the oxidation number of carbon, based on that equation, will be equal to +4, all right? So even though we don't know what the oxidation number of carbon is directly based on the rules, we can indirectly find it out based on rule number 6, all right? Any questions so far? Any questions? Any questions? Okay, so let's talk about balancing redox equations. And again, this is something you should have learned in your General Chemistry 1 lecture. I certainly covered it in General Chemistry 1. So if you were in my General Chemistry 1 class previous to this, then this should look somewhat familiar, right? Now, let me just start off by saying that when it comes to redox equations, for a few of them, relatively speaking, you can balance them in the traditional way that you're accustomed to, like keeping count of all the atoms on each side and so on, right? But for more complex ones, you can do that, but it would be very, very, long and difficult. So therefore, there's another method that you can use to balance those types of equations. And in some textbooks, they call it the ion-electron method, all right? So basically, the best way to learn this, in my opinion, is go directly into an example. So here's the example, the oxidation of Fe2 plus to Fe3 plus by the dichromate ion in acid solution. Now, let me just say that, unfortunately, not enough information is given. Let me just say that an additional piece of information that you need in this question is this, to produce Cr3 plus, all right? You need that as well in order to answer this question, all right? In order to get a balanced equation for this reaction. All right, so how do we balance this equation or how do we determine the balanced equation for this reaction? The first thing we need to do is write down an unbalanced equation based on the information provided. Now, some questions might give you the unbalanced equation already, which means that you don't have to worry about that step, right? But in this case, they give you the reaction in words, so therefore you need to write down the unbalanced equation. So based on information provided, we can identify the reactants and the products of this reaction. One of the reactants would be Fe2 plus, and the other reactant would be the dichromate ion, right? So these would be the reactants. I'm just going to write R and R here. And the products of this reaction, one of them would be the Fe3 plus, and the other one would be the Cr3 plus, right? So the reactants would be on the left side of the equation, the products would be on the right side of the equation, and this would be the result, all right? So this would be the unbalanced equation that you're going to end up with in step number 1, all right? Okay, the next step in this process is that you're going to separate this unbalanced equation into 2 half equations, right? One half equation would represent the oxidation process, and the other half equation will represent the reduction process. So for the oxidation process, it's the Fe2 plus going to the Fe3 plus, right? That's oxidation because you see that there's an increase in the oxidation number. And let me just say this, and I should have said this before, even though you should know this already. Another way of looking at redox or determining what is being oxidized and what is being reduced is that you identify which species is undergoing an increase in oxidation number. If the oxidation number increases for that species, then that species is undergoing oxidation. And if the oxidation number is decreasing for a particular species, then that species is undergoing reduction. So that's something you need to keep in mind. So that's why we can tell that the Fe2 plus is undergoing oxidation because its oxidation number is increasing from +2 to +3. And then the reduction half equation would be the dichromate forming the chromium 3 plus. And again, you can tell that this is reduction because the chromium over here has a +6 charge, while the chromium over here has a +3 charge. So there's a reduction in the oxidation number. So therefore we know that that would be the reduction half equation. Okay, so that's step number 2. Step number 2, you separate the equation into 2 half equations, all right? Okay, step number 3 is where we focus on balancing the oxygen and hydrogens, right? Oh, before we do that, we need to balance all other atoms other than oxygen and hydrogen. That's step number 3, all right? So if we go back up here, we see that the iron is already balanced because you have a 1 here, iron respectively on both sides. So that's balanced, so we don't need to make any changes there. However, in the case of the second half equation, the reduction half equation, you'll notice that we have 2 chromiums here and we have only 1 here, right? So the question now becomes, how do we balance the chromiums? And the answer is we simply put a coefficient of 2 right here, and the result would be this half equation here, right? So step number 3, very important, you balance all atoms excepting oxygen and hydrogen. Okay, step number 4 is where we now focus on balancing the oxygen and hydrogen, right? Now, what we'll be discussing here is the equation that we're going to determine for acid conditions. And then later on, we'll talk about the basic conditions. So to balance the oxygens first, we need to balance the oxygens first. So to balance the oxygens first, what we do is we add water to the side that needs the extra oxygens so that the number of oxygen atoms on both sides would be equal, all right? Now, in the case of the first half equation, again, we don't need to do anything as far as that is concerned because there are no oxygens involved. However, in the second half equation, because we have 7 oxygens on this side here, that means we need to add 7 water molecules on the right side in order to achieve the balance of the oxygens on both sides, right? So therefore, that's what we do in this case. We add 7 water molecules to this side so that we end up with 7 oxygens here, which is equal to the 7 oxygens on the left side. Then we have to balance the hydrogens. How do we balance the hydrogens? By adding H plus ions to the side, which is deficient of hydrogens, and we add enough so that we achieve the balance of hydrogens on both sides. So what that means, therefore, that in this case, we need to add 14 hydrogen ions on this side to balance with the 14 hydrogen atoms on the right side, all right? So just to recap this particular step, we achieve the balance of the oxygens first, and we do that by adding water to the side with a deficiency in oxygen, and we add enough water molecules such that the number of oxygen atoms on both sides are the same. And then after that, we balance the hydrogens by adding hydrogen ions to the side that is deficient of hydrogen. And again, we add enough such that the number of hydrogen atoms or ions on both sides are the same. Okay, so that's step number 4. Step number 5 is very important because not only do we need to balance the oxygen and the hydrogens or any other atoms, but we also have to achieve charge balance. In other words, the total charges on both the left side of the equation and the right side of the equation must be the same, right? In order to achieve that balance, what we need to do is add electrons to the side which has a higher net charge. And let me just say that based on past experience teaching this particular topic, this is where students tend to make most of their errors. They tend to add electrons to the wrong side, right? So let me just say this so that you remember which side of the equation you need to add electrons. You add electrons to the side with the higher net charge. You add electrons to the side of the equation with the higher net charge. And you add enough such that the number of charges total on the left side is equal to the total number of charges on the right side. Okay, so let's see how this works for both half equations. In the case of this half equation, right? Because you have a +2 charge here, in fact, let me do it here. Because you have a +2 charge here, and you have a +3 charge here, before you add the electron, what you do is that you add 1 electron on the right side. And the reason why I do that is because this side here has a higher net charge compared to that side. So therefore you add 1 electron, which means that you're reducing the total charge here by 1. So this becomes +2, which balances with the +2 on the left side, all right? So that's what happens in that case. Now, in the case of the second half equation, let me get rid of this here. In the case of the second half equation, right, because, let me go back up here, right? This is before you add the electrons, right? So what you do is find the total charge on each side. So for here, you have 14 plus charges, plus 14. And then you have -2, -2. So the total charge here on this side would be +12. Over here, you have 2 times +3, which is +6. And of course, water is neutral, so water does not contribute any charge to that side. So in this case, before you add the electrons, you have a total of +12 charges here and +6 on this side. So again, as I said before, what you need to do in order to achieve the balance of charges is that you add electrons to the side with a higher net charge. So that means that you add electrons to the side which has +12, right? So the question now becomes, how many electrons do you add? Well, to reduce this to be equal to this, you're going to add 6 electrons, right? So by adding 6 electrons, you're adding 6 negative charges to this side, and that reduces the total charge on that side to +6, which is equal to the +6 on the right side, right? So that's why 6 electrons are added to the left side of the second half equation, all right? So just to recap, just to make sure that you understand what's happening here, when it comes to balancing the charges, what you do is count the total number of charges on either side of the equation. The side that has a higher net charge is where you're going to add electrons. And therefore, the only other thing you need to figure out is how many electrons you're going to add. You add enough electrons to that side so that it brings down the total charge on that side to be equal to the total charge on the other side. And therefore, that's how you achieve the charge balance. All right. So the next step is very important because one thing, I don't know if I mentioned this earlier, what is true for all redox reactions is that the total number of charges, or I should say, the total number of electrons lost in the oxidation half equation must be equal to the total number of electrons gained in the reduction half equation, right? You cannot have those two numbers not being equal. As we have it right now, that's not the case, right? We have 1 electron being produced here in the oxidation half equation for this reaction right here, and we have 6 electrons being gained here, right? In the case of the reduction half equation. So now we have to make sure that those electron numbers are equalized. How do we achieve that? We achieve that by multiplying either one or both equations by certain integers so as to achieve the number of electrons lost and gained be equal. So in this particular case, we have 6 electrons here being used up. We have 1 electron here being produced. So what we would do is multiply this equation here, the entire equation, by 6, right? So basically, this is what you're going to end up with. 6 Fe2 plus to give 6 Fe3 plus 6 electrons. So now we have 6 electrons being produced here, which would be equal to the 6 electrons being lost in the second half equation, the reduction half equation, all right? And that's very important because as you're going to see in the next step, those electrons will cancel out. You should have no electrons left over in the final equation, all right? So remember, when you get to this stage, the next step would be to ensure that the number of electrons lost or gained would be the same. And you may need to multiply one equation, as in this case, by a certain integer, or in some cases, you need to multiply both equations by different numbers to achieve that equalization of the number of electrons, all right? Okay, so that's step number 6. Oh, that's the second half equation, which is still there. So basically, the next step is where you're going to add both half equations. And in doing that, the number of electrons must cancel out, right? So that's what we're going to do here, right? These are the two half equations that we have obtained so far up to step number 6. And the 6 electrons here produced will be canceled out by the 6 electrons that is gained. And therefore, there's nothing else to cancel out. And basically just write down what is left, and that would be the net equation. That would be actually, or should be, the balanced equation. And let me just say that there are some instances where there are other substances that will be canceled out. In fact, we're going to look at some examples of that shortly, all right? So that's important here. The important thing that I want to highlight in this step is that the number of electrons, or the electrons, should be canceled out. There should be no electrons left over, all right? Then we get to the final step, because even though this answer should be correct, what I would do, if I were you, is to check to make sure that everything is balanced in the final equation. So that means you'll be checking to make sure that the number of atoms of each element on both sides are the same. And not only that, you're going to check to make sure that the total charges on both sides are the same. So if we look at this equation here, which should be the final answer, let's look at the hydrogens. We have 14 hydrogens here on the left side. We have 7 times 2, 14 hydrogens on the right side. We have 2 chromiums on the left side. We have 2 chromiums on the right side. We have 7 oxygens on the left side. We have 7 oxygens on the right side. We have 6 iron ions on the left side and 6 iron ions on the right side. And then in terms of the charges, we have 14 plus charges minus 2 plus 6 times 2, 12. So when we do that, you're going to end up with 24. And then on the right side, you have 6 times 3, 18. 18 plus 6, that's 24. And therefore, the charges are also balanced. So therefore, we are confident that this would be the correct answer. All right? This would be the balanced equation. Okay, any questions about this? Okay, one more thing I want to mention here. Now, what I've described so far is in regards to acid solutions, right? The redox reactions occurring in acid solution. However, we can write down or figure out an equation for the basic solution. Basically go through all that we have just done here, but in the final step for basic solutions, what you're going to do is add a hydrogen ion for each, you're going to add a hydroxide ion for each hydrogen ion that is present in the reaction. So in this particular case, since we have 14 hydrogen ions, we're going to add 14 hydroxide ions to both sides. All right? Now, what you need to realize is that each time an H plus reacts with an OH minus, it forms a water molecule, right? So when you add 14 H plus ions to 14 OH minus ions, this will produce 14 water molecules, right? And because you have 14 water molecules on this side, and you have 7 water molecules on this side, what's going to happen is that these 7 water molecules will cancel out 7 of these water molecules, leaving behind 7 water molecules on that side, all right? So therefore, the final equation for this reaction in a basic environment is going to be 14 OH minus plus 7H2O plus Cr2O7 2 minus plus 6Fe2 plus to give 6Fe3 plus 2Cr3 plus. Oh, shoot, I should not have included the OH minus here. Take that out. Sorry about that. Because the OH minus is actually going to be over on this side, 14 OH minus. And that's it. And that would be the equation for the same reaction under basic conditions. All right? So that's basically how that is done. Okay, any questions about that last part? Any question? And that includes you guys out there in Zoom. If you have any questions, please feel free to ask. Okay, so if there are no questions, I think the next best thing to do is, what time is it? Is go through some examples, and then we call it today. So let me get out of this here. And let me, I'm just going to make up an example. I don't even know what the correct answer is going to be. Suppose you're given okay, so let's say you're given this as your unbalanced equation and you're asked to balance it. So based on what we have covered so far, what will be the first step? Let me hear what you have to say. That includes you guys out there in Zoom. Please feel free to chip in and make your contribution to this discussion. So what will be the first step? Feel free to follow, what we discussed, the rules or the guide that we covered just now. So what will be the first step? Separate it into two half equations. So what would be the first half equation you'd write down? Mn04 minus the form Mn2 plus, okay. And then the rest would be C2O42 minus the form CO2. Okay, very good. What's the next step?
Atoms other than oxygen and hydrogen.
I'm sorry?
Balance the atoms that are other than oxygen.
Right, balance all atoms other than oxygen and hydrogen. All right. So what does that mean? In the case of the first half equation, we don't need to do anything because the manganese is already balanced, right? But what do we do in the case of the second half equation? You have to balance the carbon, right? How do we do that? Put a 2 in front of the CO2, all right? Very good. Okay, next step.
Add H2O to balance the oxygen.
Okay, very good. So for the first half equation, to which side would you add the water and how many water molecules would you add?
The product side.
You're talking about the first half equation? To which side would you add it? On the product side, okay, and how many would you add? 4. All right, what about the second half equation? Mhm.
Add anything, do you?
Exactly, we don't need to add anything because we have 4 oxygen on both sides, so we don't need to add any water molecules. Okay, very good. What about, or what is the next step? After balancing the oxygen, the next step would be to what? To balance what?
The hydrogen.
Hydrogen, and how do we balance the hydrogen? By?
Adding just hydrogen ions.
Yeah, by adding hydrogen ions. So, what does that mean for the first half equation?
8
To the,
reactant.
to the reactant side, okay, very good. And again, because there's no hydrogen in the second half equation, we don't need to add any hydrogen. Okay, so the next step would be to do what? To balance what?
The charges.
Okay, balance the charges. And how do we balance the charges? By?
Electrons.
Okay, so let's see if you can do this without screwing it up, because as I said before, this is where most students make their errors, especially when learning this for the first time. So, how would you determine which side would you add the electrons?
Go with the higher net charge.
Okay, very good. So which side has a higher net charge in the case of the first equation?
The reactants.
Exactly. So what's the total charge on the left side?
7
+7. And what's the total charge on the right side?
+2.
+2. Okay, very good. So to which side would you add electrons? As you said before, on this side. So the question now becomes, how many? +5 electrons, exactly. Because by adding 5 electrons, you're reducing the total charge on that side from +7 to +2, which is equal to the total charge on this side. All right, very good. What about the second half equation? To which side would you add electrons and how many?
Product side.
Okay, and how many would you add? 2 electrons, exactly. All right, because over here, you have a total of -2. Over here, the total was 0. So therefore, to reduce this to -2, you add 2 electrons, which add a -2 charge. So the total charge on both sides will end up being -2. All right? Okay, very good. So the next step is what? What's the next step?
Equalizing the electrons.
Okay, we equalize the electrons. So how would we achieve that in this particular case? Because we have 5 electrons here and we have 2 electrons here.
You have to multiply it, right?
Yeah. So what would you multiply this by? Exactly. So you're going to end up with 10 electrons here plus, and remember, you need to multiply everything here, not just the electrons, right? So when you multiply right through by 2, you're going to end up with 10 electrons plus 16 hydrogen ions plus 2 MnO4 minus to give 2 Mn2 plus 2, not 2, I'm sorry, 8 H2O. All right? So what about the second half equation? What would you multiply that by? 5. So when you do that, you're going to end up with 5 C2O4, 2 minus, to give 10 carbon dioxide plus 10 electrons. All right? And then we add these two together, right? So the electrons will cancel out, and there's nothing else that will cancel out. So your answer is going to be, let me scroll down here. (16H plus 2 MnO4 minus plus 5 C2O4 2 minus, and then on the product side we have 2 Mn2 plus 8 H2O plus 10 CO2. And that should be the final answer. But again, as always, if I were you, I'll check to make sure that everything is balanced, including the charges. So let's do that now. We have 16 hydrogens here, which balances with the 16 hydrogens here. We have 2 manganese here, which balances with the 2 manganese here. In terms of oxygens, we have a total of 8 plus 5 4 is 20, so that's 28 oxygens on this side. And then on this side, we have 8 plus 20, so 28 oxygens on this side. So the oxygens are balanced. And then we have 10 carbons here, 5 times 2, 10. Here we have 10 carbons here, so the carbons are balanced. And then we have to look at the charges. Make sure that they're balanced on both sides. So we have plus 16 here, minus 2, minus 5 times minus 2, which is 10. So 16 minus 2, that's what? 14. 14 minus 10, so that's equal to plus 4. And then over on this side, we have 2 times plus 2 plus 4. So the charges are balanced as well. So therefore, this would be the equation for the reaction. And remember, this is under acid conditions. So let me write this down. Acid conditions, all right? So that would be the balanced equation for the reaction under acid conditions. Now, if you're asked to find out the equation under basic conditions, what would be the next step? You add what?
Minus
How many?
16.
Right, you had 16 hydroxide ions to both sides. All right? And these 16 hydroxide will combine with those 16 H plus to form 16 H2O, right? And these 8 water molecules will cancel out 8 of these. So your final answer in the case of a basic environment would be 8 H2O plus 2 MnO4 minus plus 5 C2O4 2 minus to give 2 Mn2 plus 10 CO2 plus 16 OH minus. And this would be the equation for the reaction under basic conditions. All right? Okay, any questions about this? Any questions? Okay, is it okay for me to erase this? All right, let me do that now. Let's do another example. And this time I'm going to not say much, because I want to hear you guys articulate what the answer should be. And again, I'm just making this up. I'm not even sure if this reaction will take place, but just for the sake of practice. Suppose you're given NO3 minus plus S2O3 2 minus to give N2 plus S4O6 2 minus. Okay, I think that should work. All right. So let's say you're given that. What would be the first step? Okay, so NO3 minus the 4N2 and S2O3 2 minus to form S4O6 2 minus. Okay, very good. Next step.
Balance all the atoms that aren't the oxygen or.
Okay, so what does that mean? What does that mean for the first half equation? What do we need to balance, if anything?
The two coefficient on the NO3.
Okay, very good. And what about the second half equation?
The two coefficient on the S2O3.
Okay, very good. All right. Next step.
H2O balance the oxygen.
Okay, so what does that mean for the first half equation?
3 H2O to the,
You sure of that number? Hint, hint.
oh, sorry,
Mhm,
6.
exactly. So you had 6 water molecules on the side. What about the second half equation?
Add any H2O.
Right, you don't have to add any water to that. Okay, very good. Next step.
Then balance the hydrogen.
How do we do that?
Add hydrogen ions.
How many? And to which side?
12 on the reactant side.
Okay, for the first half equation. And again, because there's no hydrogen in the second half equation, we don't need to be concerned about doing that. For the second half equation. Okay, next step.
Then we have to add electrons to balance the net charges.
Okay, so what does that mean for the first half equation?
We have to add electrons on the product side.
For the first one, you sure? What's the total charge on the left side for the first half equation?
S3.
For the first half equation? Oh, my bad. I'm talking about this one right here. This
Oh.
equation,
Oh, whoops, I was looking at the wrong one.
right? Remember, this is what we started off with. Let me,
Oh, yeah, sorry.
right. Okay, so this is what we're focusing on right now. What's the total charge on the left side of this equation?
0.
Nope. We have plus 12 and then minus 2,
So
because you have this 2 multiplied by that. So this would be plus 10 on this side, right? And how many charges do we have on the right side?
none.
0, right? So to which side would you add electrons and how many?
The left.
To the left side, how many would you add?
10.
10 electrons, exactly. All right? What about the second half equation? Which side has a higher net charge? What's the total charge on the left side? Minus 4. What's the total charge on the right side? Minus 2. So to which side would you add electrons and how many would you add?
Right.
How many?
2.
Exactly. All right? Okay, very good. So now that we have done that, what's the next step? How do you achieve that? By, in this case,
We only have to multiply the second equation
by what?
5.
Exactly, so you multiply this by 5. We're gonna end up with 10 S2O3, 2 minus to give 5 S4O6, 2 minus, plus 10 electrons, right? So let me just scratch this out just to avoid confusion, because what you're gonna do now is add this equation to this equation, right? And of course, again, the electrons will cancel out. And you just write down what is left, which would be 12H plus 2 NO3 minus plus 10 S2O3 2 minus to give N2 plus 6H2O plus 5 S4O6 2 minus. And that should be the final answer. Again, this is under acid conditions. All right. So again, as I said before, always check through to make sure everything is balanced. 12 hydrogens, 6 times 2, 12 hydrogens. So those are balanced. 2 nitrogens, so that's okay. We have 20 sulfurs here. And we have 5 times 4, 20 sulfurs, so the sulfurs are balanced. And then in terms of the oxygens, we have 6 oxygens plus 10 times 3, 30, so that's 36 oxygens on this side. And on this side, we have 6 oxygens and 5, 6 is 30, so we also have 36 oxygens on that side. So the equation is balanced. All right. Okay. There's one more example I want to do, but I'm not sure if we'll be able to finish within the time allotted. In the meantime, what I'm gonna do, as I said before, I forgot to bring down the copies of the assignment for this chapter. So what I'm gonna do for you guys is to publish that assignment now. And let me just check something out here. So based on what we have covered so far, you guys should be able to do questions 1, 2, 1A, B, C, D, E, F, G, H. Okay. Basically number 1, right? A through H, all right? So you should be able to do those. Again, if you're encountering any difficulty while doing them, please feel free to call me. Yeah, and that's it, all right? So you won't be able to do anything else until we cover those topics in the next class. All right, so that's it for today, folks. And I'll see you guys. I think I'll see all of you here in lab later on. Okay. Oh, okay. You can look that up online.
This is the only value I got online.
Okay.
We don't send that, so it's one thing. Online it says that,
No, but you're looking for the gas, right? That's the one, is that,
that's.
no, use the one on the table here.
So, not that one.
Yeah. Mhm. 'On to the lab. Lab should be fun.
And I got all my lab questions done.
Mhm. Mhm.
Since there's no three in it, I would just do 3 times what S was.
I'm sorry, read that? For number one.
I'll have for 3. You see how this one was graphite?
Okay, yeah, so basically it says calculate the standard entropy change. Okay, so basically you look up the values for these two, add them together and subtract the value for these, for that one. So, yeah, you get those values from the table.
Good.
Oh, by the way, you guys out there in Zoom, I'm signing off right now.
This graphite is 2.377.